All right, legends, this is Mr. Mays. Wonderful to have you here, coming to you through the digital space. And today we're going to be looking at lesson 9.2, which is going to just be chi-squared tests. Now, there are two of them in question that we'll be dealing with, and neither of them are goodness of fit tests. Now, the thing I want you to do right now is go ahead and pull up our slides. And you'll note that the slide number 7, the chi-squared goodness of fit slide, reminds us that goodness of fit, which is not just considered a regular chi-squared test, the goodness of fit one is just for a single variable and a single population. And the question becomes, what do we do if we want to use more than one variable or more than one population? Well, on slide 8, we figure out that these are the two tests we're learning about today. There's chi-squared for independence, also known as chi-squared for association, and chi-squared for homogeneity. Okay, now luckily for AP, you can just say chi-squared for both of them, right? And AP won't matter if you differentiate, or won't care, I should say, if you differentiate. Now, if you look at slide 9, we get a feel for what an example might be of a chi-squared for independence two-way table. And for all of this, we're going to be working with two-way tables. Why? Because they are a wonderful way of showing multiple categorical variables or multiple populations presenting a singular variable across those populations. Now, the reason I know that this table on slide 9 is an independence one is because independence, and this says it on slide 8, independence is when we're doing more than one variable, right? Multiple variables, but one single sample. So one sample. On the other hand, homogeneity is when we're doing more than one population and therefore more than one sample, and normally one variable across that sample. But we can do multiple. That is available to us. So we have all this data on slide 9 for an independence chi-squared test, and it's basically just looking at age ranges and how they prefer various shipping methods. Okay. Slide 10 reiterates this idea that we're looking at two categorical variables in a single population. And of course, we go through phantoms. Now, I'm going to leave it to you to go through the various slides and map out what we're looking for a chi-squared test. But just a few things to note. On slide 12, we see the null and the alt, right? The null is there is no association between the two things, aka thing 1 and thing 2 are independent. Variable 1 and variable 2 are independent. And then the alt is, of course, that there is an association between thing 1 and thing 2. Therefore, they are dependent. And for this, of course, we're going to use phantoms. For these, the p and the h function together, and we just set up our null and our alt, as I've said previously. And then on slide 12, you will note that that is where that information is found, right? So the p and the h come together because when you give the parameter, it should be present in your hypotheses. You should write your hypotheses out in common language. Now, the A, on the other hand, is exactly the same as it was for chi-squared goodness of fit tests, right? We have random. It must be stated in the problem. We have independence. And what we're suggesting there is just ensuring that the samples are independent. And when we do that, we will just go through and do 10 times our sample size and hope that that is less than the total population we are measuring. So we want independence among the subjects, right? And then we have to do expected counts. Remember, we are not doing normalcy here, just expected counts, and they all must be listed. List all of them. And they must be greater than or equal to 5 each. Okay, now how do we do that? Well, the wonder of this is almost everything else that I do with you now, I'm going to do on my calculator emulator. So we are on slide 13. We're moving on to slide 14. There are directions here for how to find expected count. But let's go together, shall we? I feel like Miss Frizzle. Whoosh! We are now going to go on a totally new adventure. You will note my TI-84 is now wonderfully present for us. Ooh. Let me clear it. I don't want to use tan. That does not seem like the move in question. Okay? Now, here's what I'm going to do. I'm going to go ahead and set this up. I'm going to pick some random variables. Actually, for the sake of argument, let's go through and use the table on table 9, right? Let's on slide 9, I should say. So step 1, I'm going to solve a chi-squared test. This will be true no matter if I'm doing one for independence or if I'm doing one for homogeneity. right? So this is specifically for that. I'm going to start by going second, and I'm going to do matrix, which is x to the negative 1. I'm then going to go over to edit. And matrix A is going to be my matrix. I'm going to do a 4 by 3 matrix. So I click 4, enter, 3, enter. Now I'm going to put my data points, the very same ones you see on the table on slide 9. So 47. And you're going to notice for these data points, as I put them in, I am not putting in, right, any of the totals, because those don't count as actual data points. Those are values we find that allow us to make conditional observations. However, none of them in and of themselves are actual data points. So we're essentially going through and just putting in the 4 by 3 for the table. Remember, of course, that the table is set as row by column, right? That's the way that it's titled, so 4 by 3 matrix. So once you've put your matrix observations in, these are, of course, this is your observed data that you've just put in, okay? Now here's what you'll do when you want to run your chi-squared test, and also when you want to find your expected counts. You have to actually run the test to find the expected counts. We're going to go to stat now. We're going to go over to test. For both chi-squared for independence and chi-squared for homogeneity, oh goodness, we go down to tests. I was in calc. We go down to option C. Not option D, which we've used for goodness of fit, GOF, but option C, chi-squared test. Click enter. Auto-populated should be matrix A. Matrix B is going to hold our expected values, okay? It's going to hold our counts that we're looking for, our expected counts, once we click calculate. And lo and behold, I have my chi-squared and my p-value. Please note that it is 2.3 times 10 to the negative 9, so it's really 0.00000000023. Okay, so a very small p-value. Just as always, we will, because it's so small and it's less than an alpha of 5%, which I haven't stated an alpha here, so we can presume it's 5%. We are going to reject the null here. There will be convincing evidence for dependence between age range and preferred shipping method, right? Our degrees of freedom is 6. What you will note is degrees of freedom are take the number of rows minus 1, multiply that by the number of columns minus 1. So this was 4 by 3. 4 minus 1 is 3. 3 minus 1 is 2. So 3 times 2 is 6. Those are our degrees of freedom. Okay. Now here's the best part. For our expected counts condition, you will go to second matrix again. But you'll notice now the B matrix has 4 by 3 in it. Go over to edit, go down to B and click enter. Those are my expected counts. And what I would do for a problem is I would note them all and say blank, 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 all greater than or equal to 5. But I'm noticing something, legends. Bottom right and bottom left corner present two values that are not greater than or equal to 5. We have 4.76 and 2.18. So actually this is an example of one that you could not do because your expected counts have failed, okay? If they are working, you should list every single one of them. If it's not, list the ones that are not working and state them that the following values are not functional and therefore they do not meet our expected counts and we cannot run a chi-squared test. Okay, going right on back to where we were. We've done almost everything that we need to do. I just want to go through a couple of the differences that you'll note between chi-squared independence tests and chi-squared homogeneity tests. On slide 10, you'll see everything that we've said already. We've pushed through. I shouldn't have gone back to slide 10. That's not what we're looking at. We now want to go to slide 15. Right? For an independence test, you will say chi-squared test for independence, but remember, you can literally just write chi-squared test. You could write that for either one. Just don't write that one for a chi-squared goodness of fit test. You have to say chi-squared goodness of fit for that particular test. Slide 16 walks you through all the stuff you already know, plus it reminds us that degrees of freedom for these particular tests are going to be rows minus 1 times columns minus 1. That's because we're running expected counts for all of them. Slides 17 and 18 slide 17 walks you through the calculations we just did, and then slide 18 reminds you of your conclusion. Now, this conclusion will hold for both of our situations, but you know how it goes. If the p-value, just as always, is less than the alpha, then and you should say both of these things, reject the null, and you will say convincing evidence in context for the ha. And then, of course, the opposite holds true. If the p-value is greater than the alpha, then we fail to reject the null. Do not accept the null. Do not find convincing evidence for the null. And we find convincing or we find no convincing, I should say, evidence for the alt. Okay, and remember to put it in context. Slide 19 reminds us that the main difference between independence chi-squared tests and homogeneity chi-squared tests is that in homogeneity, we have one variable, but several populations. And then slide 20 runs through that difference one more time for the cheap seats. Slide 21 gives us our null and our alt. And those homogeneities and their hypotheses are stated on slide 21 with clarity. There's no difference in the distribution, or there is difference in the distribution. The null is that there's no difference. The alt is that there is difference. The difference is the thing we want to show. We have the same situation with expected counts, etc. Just be sure that you say treatments and samples, because we have multiple of those for chi-squared test for homogeneities. And then on slide 22, I remind you, T, O, M, and S are all the same as they were for chi-squared tests for independence. Remember on slide 25 how to interpret a p-value in context. And remember that chi-squared is more of a general test. We do it as a starting point. It gives us an idea if there's something to look for, if there's something to dig deeper for, and then we'll do a 1 or a 2 sample test accordingly. 1 sample test if we are looking at a chi-squared test for independence, and a 2 sample if we're looking at a chi-squared test for homogeneity. Finally, you'll see on slide 27, the main difference that you will find between a chi-squared test for independence and homogeneity is simply answer C, the number of samples. 1 sample for a chi-squared test for independence, 2 for one for homogeneity, or multiple if you're doing one for homogeneity. I'm so proud of you. I know this was sort of a really, really quick lesson, but the good news is, the reason it's quick is it should feel fairly straightforward given all the magical things we've done this year and all of our immense knowledge applied to the task at hand. I'm proud of you. I'm thankful for you. I hope this all felt clear. If not, reach out to me on Remind. But all said and done, I remain so thankful to be your teacher. Study up, be ready. And this is Mr. Mays signing off.